please close your microphone and camera and video for now. And we start today with two young researchers that are going to speak. So the first one is José Antonio Villa from Instituto de Matemáticas UNAM, and he's a PhD student. Please, José Antonio, you can start.
So thank you very much to the organization committee to give me the opportunity to give this talk, to give this talk. So I'm going to talk about hierarchical control of the semilinear height equation. And so the first ideas that I am going to talk is about cooperative games. And cooperative games began with Gabriel Kremer and Daniel Bernoulli. And John Nash and von Neumann give the first notion about cooperation between participants in a game. And these ideas are going to be used for hierarchical control. And the idea is that controls are going to be seen as a participant of a game, and each one of them are going to take roles in the game or in the control problem. So the classical hierarchical control is I'm sorry, the Zoom screen is I can see my presentation.
We are seeing it.
Okay. The classical hierarchy for the height equation is that given two controls, called the follower and the leader. And the idea is that the classical problem is that the leader control must control the solution approximate to zero. And the follower control so the functional that the follower should minimize is this, and given an objective function, we should find a minimizing follower control that minimizes this functional, and that the solution is not going too far from an objective function that is given by YD. And when the follower control is calculated, and a leader control should be found such that the approximate controllability is fields. In the 1940s proved the existence of a control of a leader control such that the approximate controllability is satisfied. And Araruna solved the problem with this condition in the open sets and introducing some weights. And with this new introduction of weights, the nullity of the problem can be solved. So the problem that was an introduction to present our work. So the problem that we're going to study is for the height equation, again, for the same two controls, but now the follower control should satisfy the null controllability problem, and the leader should minimize a functional. And in the classical problem, the objectives were inverted. So this is going to give a new difficulty for the problem. So the first idea is that, okay, the statement for the follower control is that it should steer the solution to zero in a positive time, capital T. And the intro that I'm going to present after, this is equivalent that the follower control is going to minimize a functional. So null controllability is going to be to minimize this functional, because Okay, and the leader control should minimize this functional. So for the follower control, I say that the null controllability was equivalent to minimize the functional. So this is because we introduce in the functional these weights. So these weights, the denominator of the fraction here are function that go to zero in capital T, and it's like a split function. It's bigger than 2 capital T 2, and in this side of the interval is given by this expression. So when T go to capital T, this go to infinity, and this make that the functional, that the solution goes to 0 in capital T. So this is the idea of this method, to introduce this kind of weights that were given by Fursikov and Imalyunov, and this is going to force the solution to go to 0. So I'm going to introduce these new spaces that are weighted spaces, and this new bilinear form where Li is the operator, the height operator with with a potential. So and these spaces are going to be L2 functions with these weights that are the weights that I give before. So the first problem for the for the semilinear problem is to solve the linear problem with f it has this potential in L infinity. So and we are going to take the same condition over the open sets. So the role is going to be, again, f should control to 0 and v should minimize a functional. So the first result is that the follower control is going to be given explicitly by this expression, where P is a solution of this equation. So this functional is given by this expression, and this bilinear form is that I gave after, is this one. So y is going to be given by this expression in function of the solution P. So the aim of this theorem is to prove the existence of a solution of this equation. And for this, we are going to use the Karman inequality. So this Karman inequality that involves the weights that I give before is going to give the coercivity for the function, and this is going to give us the solution for the problem. So Karman inequality is going to give the coercivity of the functional, and the remainder task is to prove this the continuity of the functional L. So for this inclusion in this space, we can conclude that the functional L is continuous. So the equation that involves the bilinear form is equivalent to this four-ordered equation, and this comes from replacing the identity where y, the solution y, was given by this expression, and that's what replaces it in the original equation and gives this form of the solution of the equation. So this problem is equivalent to this fourth order equation. And the another theorem is to characterize the leader control, and this is again the explicit form of the follower, and the leader is given by this expression. So says that the leader control is given by this sum, where phi hat is given by this expression, and psi hat is a solution of this equation. So where this expression comes from, or why we are defining psi hat by this form. So when we are going to, first we are going to introduce these systems. And the idea is that when we want to minimize the functional for the leader, we are going to we are going to find these integrals. So we need to change the domain of this integral for a domain for this integral, which is the domain for the follower. So the expression that gives the psi hat function is precisely the expression, the equation that we need to change the domain of the integral in order to change this integral for an integral of this form and have the solution, and this gives the solution for the leader control. So once for the linear case the solution is given, the idea is to apply the to use these results for the semilinear case. So for the semilinear case, the idea is to apply a fixed point theorem to give a solution for the follower control and a solution for the leader control. So for the follower control, we are the linear problem is solved, and apply a fixed point theorem and use minimizing sequence to verify that the functional is going to have a solution. So once that the follower, that the problem for the follower is solved, we need to apply again a fixed point theorem for the leader. And this is done by Calzavara, Fernandez Cara, Teresa, and myself. And in a paper that is now in revision. So for the semilinear Heyde equation, the problem is given by a fixed point theorem. So another problem is a state where one of the controls is given in the boundary. This problem in the boundary I'm going to present only results for the linear case, because for the semilinear case we are working in that problem. So now we are going to take that the follower control is in the boundary and the leader control is inner controllability. So for this problem, we are going to use again some techniques that are similar to the problem that for the inner controllability, when both of the controls are inner controls. So again, we are going to we introduce these new spaces that are L2 functions in each of the domains of the controls, and with these new weights that are given in a similar way of the weights that I give for the inner control problem. So the idea for these weights is that going to be are exponential that go to infinity when t goes to capital T. So this is going to follow the same idea that the solution should be go to zero when t goes to capital T. So the statement of the problem is again that the follower control should fulfill some null controllability problem, and this is going to be to minimize this functional. So again, here the solution is affected by the weight. So if the follower control fulfills the equation, fulfills the minimizing property, this forces the solution to go to zero in capital T time. And again, the leader control should go to should minimize the dysfunctional. And again, the solution should not go too far from the objective function given by YD in the open set matcal OD. So for this, we are going to introduce. Sorry. For this, we are going to introduce this bilinear form. So the bilinear form is similar that given by for the inner controllability problem. So I'm going to go back. So the bilinear form M was given by this, And now because we have a boundary value problem for the normal derivative in the boundary. So the idea for this is the same. We are going to have we are going to use a Karman inequality in the boundary for this expression. So the difficult for the boundary value problem or for the follower control in the boundary is that we need to have new Karman inequalities, but now that involves the terms in the boundary. So for by the unique continuation property, we have that this bilinear form is a norm in rho 0. In P0 was the function that R0 in the boundary of the cylinder given by the omega cross product of the interval 0t. And we are going to introduce these functions. This function is going to fulfill these conditions. And again, we introduce these weights that are going to go to 0 in capital T and are going to be greater than half T capital in the interval 0, half capital T. So, sorry. Again, for this problem, we have this Karman inequality. So this Karman inequality involves, okay, we are comparing this integral, but now we are comparing with this bilinear form, and this bilinear form is in the boundary. So now the Karman inequality is going to be an inequality that involves the boundary terms, and this is going to give us the coercivity. Okay, the follower control gives again is given explicitly by this expression, and the solution is given by this expression. But now the follower control is given by the normal derivative of the function p, where p is a solution of this expression. So again, Karman inequality is going to give us the coercivity for this bilinear form, and we can say that this equation have a unique solution p in the space B, that is the closure of this with the norm induced by this expression. So the difference is that, okay, to prove the continuity for this expression, that is the right hand side of the equation, we need to estimate in the boundary these integrals, and we can say that the function p is bounded, and this gives us the continuity of this side of the equation, and we can apply Lax-Milgram theorem, and we have a solution for this equation. And for the follower leader control, we are going to linear form is going to be involved again. And before I talk about the explicit form of the leader, it's necessary to prove the continuity of this functional. So using estimates in the boundary, the trace theorem, we can have these estimates for the functional f, and this is going to be useful to solve to apply Lax-Milgram theorem again for the follower control. So for the follower control, the explicit form is given. Okay, we can characterize the follower control, and the leader control is going to be given by this expression. And now the expression for the leader control is given again by the sum of this function. One is the solution for this equation, and this one is again the solution for this integral form. And this integral form, the idea is to apply follow the same ideas when we have to change the domain of the integral in order to have an explicit form of the leader. So this expression is use it to change the domain of the integral, as was done in the inner controllability case. And we have the problem where the two controls are, when the follower control is in the boundary and the leader control is in an open set, we have this expression for the leader control. And another problem is where both of the controls are in the boundary. So again, now we introduce these new weights. These weights are given by estimates in the boundary. And again, the roles of the controls are the same. We should minimize this functional, that is null controllability. The leader control should minimize this functional. And the results are similar for the follower control. Again, the follower control is given by the normal derivative of this function that is given by this bilinear form, and that involves here the normal derivative of the here's a mistake. Here's a p apostrophe, and the solution is again given by this expression. And we can use Karman estimate in the boundary and use this trace theorem for the right hand side of this expression. We have this inequality give us continuity for the functional, and it allows to apply Lax-Milgram theorem. And for the follower control, for the leader control, again we have a similar expression for the leader. And for the follower, and for the leader control, we have, again, now because the leader is in the boundary, the solutions are going to be the normal derivatives of the function q that is given by this equation, and c that is given by, again, an equation of the bilinear form that is given by this integral. So again, the normal derivatives in the boundary are involved for this problem. And so the problem, the inner controllability problem, where and the semilinear case, when the follower control is in the boundary and when both of the control are in the boundary, are solved here. So the remainder task is to try to solve the semilinear case when both of the controls are in the boundary, and the semilinear is a superlinear function. A superlinear function is the function that increases like a logarithm. So the reminder task is to solve the boundary problem for the semilinear case when the semilinearity is given by a superlinear function. So thank you for your attention.
Thank you, José Antonio. We have time for one or two questions. I don't know if somebody wants to ask something. Nobody? Well, Pedro González Casanova says, good talk, I have to lecture, thanks. Okay. So can you tell us more about the difficulties when the control is on the boundary to get the semilinear situation? to solve the semi-linear situation. I don't know if you are hearing me. Mauricio has a question. So please, Mauricio.
You listen to me? Yeah.
Yeah.
And thank you for your talk.
Your daughter too.
It was a very interesting talk. I'd like to thank everybody for the opportunity. My question is related to the fact that what do you think about for practical purpose? What's the best thing to do? If it's best to put the controllability of objective to the leader or to the follower? I mean, there's some way to measure that to see what's the best thing to do. I mean, for practical reasons.
I don't know if José Antonio is there. He just...
maybe he left.
He left.
I don't know. I don't see him. I think he's not here. I don't know, Mauricio, this question. What is...
Well, maybe numerically, I don't know. Maybe you build both problems and see which one by taking the same information.
Okay, he's there.
But
I really don't know. What do you think, Enrique?
Well, I'm not sure to have understood the question. Is
which is better?
If I have understood, what is better? Yeah.
In a practical situation, it's better to first.
Sorry,
I think that this
is.
Imagine
that you have a real problem that you want to build this situation. Which one should you apply? I don't want to answer, but at least it's possible to know something that it's a possible way to do it.
I think, José Antonio is there.
Yes, but he didn't hear the question.
Okay, I think that it is more natural to do the contrary, to control first in the optimal control sense, and then to drive the solution to zero. I think this is more natural in general. And I also know that what he has done here is more difficult, because he has had to select the follower in a smaller set, because he has to use a more restrictive functional for the first step, for the step of. So this is technically more difficult and probably less natural than the other possibility. But this is only, I think that it will depend also on the particular objective that we have in mind. No? This is what I think.
Thank you, Enrique.
I don't know. Well, thank you, José Antonio.
Thank you.
We continue with the next talk. So, Enrique, you present Gilcenio, please.
Okay. Well, Good afternoon again. I'm going to present Gilcenio Rodrigues, that is now in Piaui, in Teresina, more precisely. He has been a student of Wagner Araruna before in João Pessoa. And then he has passed some time here in Sevilla with Manolo González Burgos. And now he's in Piaui. So welcome and thank you very much for accepting to give a talk here. And he's going to speak about the boundary controllability of the one-dimensional phase field system with one control force.
Okay, thank you, Enrique, for the invitation to give this talk. I'd like to point this is my first time I do something like that and talk in English. I hope you all understand and you all take some interest for the problem. This is a work made for my thesis that was in collaboration with Manolo when I was in Sevilla, and it talks about some properties of the controllability of the in one dimension. A phase field system describes the level of solidification or melting of some material when we consider the temperature to be acting on this material. The whole difficulty here is to prove such controllability when we are acting with just one control, and to become more difficult, we want to prove these properties for a control that acts on the boundary. This is the model of the system. Here is this phase field system. The variable theta stands for the temperature of the material, and the function phi is the phase function. This function, this model is due to Kajnaup, and that's the way that we call it's Kajnaup type of system. In his book, we have the modeling of the system, and if you can see here, we have some constants like c, tau, and rho to be some physical meanings. We choose to not to assume that all of them have the value of 1 to simplify the equation, but to put them there and see how that constants, how that properties of the material, how the physical properties of the material can interfere in the controllability. And the answer that we got was that depending on the material, depending on these constants, we could not control this problem. They have to fulfill some assumptions, right? I organized the talk first talking about the problem, and then going step to step to explain for you how you can prove how hard the technique is, how the strategy to prove the controllability results that we achieved. Okay? So this is the problem, and as you can see here, we are placing a control at the temperature, at the left boundary of the temperature. And the system is clearly nonlinear, since we have on the right-hand side of the first two equations a function that have the power of 3. And something I'd like to point is that the phase function doesn't have an explicit physical meaning. In fact, the meaning that it assumes is when the function gets the value -1 or the value 1. We say that the material is in liquid state when the function stands for the value of -1, and when the function phi have the value 1, we say that the system is all in solid state. The material is all in solid state, right? this characteristic is due to the model of the system. And for the controllability view, we all try to drive the solution at the final time to 0, but in our case, the 0 to be achieved by the phase function have no physical meaning. It's not interesting to think in driving the system for the phase to be 0, because that would mean that the material would be in the mushy state, mushy form, so not even solid or not even liquid. So the interesting problem is drive the temperature of the function of the system to 0, and at the same time to drive the material to a one state on all the material, or totally on the liquid state, or totally on the solid state. So we develop, we present our problem, trying to achieve then the 0 for the temperature and some value C for the phase function, where C could be -1, 0, or 1, right? We developed all the calculations for a generic C on the set. Well, so our problem is then to try to drive the temperature with a choose of some control in L2 to 0, the temperature to 0 at the final time T. This choice of not trying to put the function, the phase function to 0, one is physical, as I explained, and bring it turns the problem more interesting. Right? Actually, we would try to drive the solution, the phase for any value that we want to achieve. Right? Any value doesn't have a practical physical meaning, and doesn't turn the system where it's interesting to study. Right? Okay, that's all. To do this, as I pointed before, we have 3 main difficulties. Try to control a system with one control. That's a system with 2 equations, and it will be more likely to prove the controllability results, the new controllability results, if we are applying two forces at the 2 equations. But taking a look in the equation, when we choose to solve this problem with one control and place the control at either the equation of temperature or the phase equation, we will choose to put on the temperature equation, because it will be more likely to it would make more sense to do that, since we can imagine that the control is a source of heat that can cool or can heat the material, but the phase, what would be a control that we act on the phase. We can physically act on the phase. So I'll choose to put the control on the temperature. What's that? That brings a difficulty, since boundary control problems are more difficult to deal, right? And the third difficulty is that our system is a nonlinear problem. So we have to use some technique, some fixed point technique, for example, to deal with such controllability. And the techniques that we have today are we pay a cost to apply that as having only a local no controllability. Okay, so that's the system that we present before. And as to make sense also, we ask the function to be in state C at the beginning of the problem, and then time 0, the phase is on both sides in the same state. There is material at the borders are both on liquid state or both on the solid state. The middle of the material doesn't matter. But for formulation of the problem, we ask to the borders to be at the same state. And at the same state that we want to finally drive the system. So we are used to solve control problems, driving both solutions of the system to 0. As more a question of being easier to deal with the problem. So we perform a change of variables, trading the phase for a phase minus a constant C. And the problem, the original problem, will become the second problem, where the initial data are all 0, and we also want to drive the temperature, and now in this new phase function, both to 0. Here are our nonlinearity are still of power 3 for the greater power, and we can write system in a vectorial way. So the presentation and computation is become more easy to do. We see here that the metrics of diffusion have the diagonal with the same values. That's important for what we are doing next. And summarize our problems is then to drive the solution of this vectorial system. That is the solution Y that contains both of the temperature and the phase function to 0, assuming that the initial data are small enough so that happen. Want to prove the existence of such control. The ideas of using here are ideas that we looked in different materials and put them together so the whole proof to work. So what we will do here? First, we'll assume that the nonlinearity is 0. That is, we will deal with the homogeneous linearized version of the system and try to drive the solution to 0, try to find a control, and then we'll use a technique where we use the homogeneous problem controllable to a problem, non-homogeneous problem, that is a problem with a source of the right side of the equation to drive this problem to 0. So we can use a fixed point to change the source that doesn't depends on the function y to the nonlinearity, right? So the steps are there. Control a homogeneous linearized system, then control a non-homogeneous linearized system, then apply fixed point to control the nonlinear system. Okay, so let's talk about the homogeneous system, the linear case. A second. Sorry. Phone was ringing. Sorry again. So we want to control the system, that is, we want to prove the proposition. We have solution, of course, for the system. We want to prove the controllability, and we start analyzing the approximate controllability. And we have found that to control this phase field system, this linear version, we need this condition, a condition that must be satisfied for the xc, tau, and rho, that is for the coefficients, for we have the approximate controllability. If you see the no controllability will only occur if the approximate controllability occurs. So this is a way to verify if only knowing the coefficients, if you can, or if you cannot actually control the system. There's a catch here, because it's we have to check innumerable ways, but infinite ways, infinite expressions, so we can say, we can prove that the system and it's not approximate controllable, or for the system is approximate controllable. Well, this condition arises when we try to make the eigenvalues of the operator L as the operator associated to this equation of the system. When you try the eigenvalues, make the eigenvalues have geometric multiplicity 1, we get this condition. But as I said, it becomes a condition to verify if the system is not null controllable. But for approximate controllability, it's a equivalence. But some computations can be made and show that this condition doesn't need to be checked this infinite number of times. Actually, it only need to be checked a finite number of times. And there's a way in where we can calculate actually how many times this condition must be checked, so we can say that this will happen for all k and l or not. And it's a good result, since this means that if we have in hands the coefficients, the physical coefficients of the system, we can put the values in the computer, and the computer will say to us that this condition can be satisfied or not. This can be made because we also can have an estimate of how many times it can be checked. This condition can be checked. So it's probably a computational condition to answer about the controllability of the phase field system. But about the null controllability of this phase field system. Remember that this information is for the linear system. It doesn't mean that the nonlinear system won't be controllable. Well, about the null controllability, we need more information about the eigenvalues of L and star to guarantee the results, to apply the technique. We don't know till now if the conditions that we ask for the eigenvalues are decisive to have or not the controllability, the null controllability. We'll have the certain that we need this condition to apply the method, right? Well, then together with this condition 5, we ask one more condition. This condition is also associated to the eigenvalues and eigenfunctions of the operators L and L star. I'll be back here. Let's see what conditions are that. In a standard way, we can prove that the condition of the function assume the values of 0 at the final time the existence of a vector that can drive the solution to zero is equivalent to this equality. And it's equality holding for all the functions that are solutions of that adjoint system of 4 associated to the eigenfunctions of the operator L star, since we can prove that they are bases for H0, 1. Actually, we can extract a basis for H minus 1 also. So this condition is equivalent to have y and final time t equals to 0 can be computed. This expression here can be written like that, in a way that this condition becomes this other one. All must be fulfilled by k infinite times and j 2 times. So that if we rearrange this condition, what we are looking for is actually the function v that will satisfy something like this with this constant. This constant is what we get when we place all that part that's not in the integral for the right-hand side of this equation and together with what already is in the right-hand equation, right-hand of the equation. So this is actually what we try to find, a control that every time that you make the inner product in L2 with the exponential of minus of the eigenvalues of the operator of the system, will give one value, one desired value. It will happen for us that this is also a bounded sequence. And it doesn't matter the j or the k, we have a uniform uniform estimate for the system. So this is the problem, this is the moment problem. How to find a control that every time you multiply for a family in K and J, give one desired value. Well, that is to say we're looking for a B-orthogonal family. A B-orthogonal family to construct such control. How? Well, we can write the control in this way with the coefficients that we want to obtain here. And if these functions kq, qk are B-orthogonal to the family of this exponential, it's clear to say that when we multiply in the inner product of these two functions, we will obtain each of these ck. So there are results and variable results about B-orthogonal families that say something to us about obtaining these B-orthogonal families. So if the eigenvalues satisfy some conditions, we have these B-orthogonal families. But we have a catch here, is that we also want the control to be in L2. So we need this series to converge in L2. It means that since this value is also null, this other value is also null as this, then the B-orthogonal family will be responsible to make the series converge. So they have to satisfy a very good bound so that the series converge. And one result that answer that gives us what we need, this good bound can be achieved if you ask the family here of the eigenvalues of the operator L to satisfy these conditions, these gap conditions, together with a numerical condition. So to fulfill this result and have good bound for the the orthogonal family, we will, together with the condition 5, ask this other condition. This first one condition, if you remember, is the condition to the approximate controllability. The second condition will be added so the B orthogonal family have this very good bound. With these two conditions, we can calculate a bound for V. Actually, writing in this form, it's a summarized form of what's written here. This CK functions have a boundary like that, being bounded by the initial data, and the B orthogonal family have the boundary given by the lemma, so that we combine the two of them and get that V can be bounded by the initial data, that is V is now true, but with this very important bound by V of V by the initial data. This is very important. It's a cost, a bound for the cost. It means that this constant we bound the cost of the control. This condition saying that V is null true, together with this existence, we solve our moment problem. This problem of existence function V null true that satisfy this condition. Then we proved this theorem that under these two conditions, the linear system can be driven to zero with a control with such estimate. Some remarks about the conditions. The first condition, the approximate condition, as I told, is important because it's a necessary condition for the no controllability. Sorry. And the second condition is what we can say about it is that if the condition is not satisfied, we cannot guarantee the controllability because of a technical fact that is the eigenvalues of the operator L will concentrate. They cannot be put apart. Remember that the lemma asks for the operators, the eigenvalues to be apart. But if the second condition, if this condition is not achieved, it's not fulfilled, then we cannot have, we're not sure about if possible. In fact, other results say that we have a minimal time to controllability. There is, if the time is very small, the problem may not be controllable. That is all other study, and have to look for this minimal time. You have to observe if this minimal time is really zero, no. But what seems to be is that this minimal time will depend also on the coefficients. So the previous answer that I have to say to give to you is that the material can interfere in the controllability. Well, I need to go fast. Since we have the homogeneous problem controlled, we use this reference, the work of Takahashi and Tuxna, to, with these ideas, place a source that need to decay exponentially and still guarantee that this problem with the source can continue to be controlled, no controlled. The source must be in the space F. It's L2 weighted space, and it will become that the control space will be also a weighted space as the solution of the of the system will also be in a weighted space. The weights depends on some constants A and B that we don't choose in the first moment. We will choose it later so we can be able to prove the fixed point theorem. So the constant will be used for the fixed point, but following the proof that the system can be driven to zero, actually we prove that the control have an estimate zero for the initial data and the source of this type, and the solution in the space y0 is also estimated for the initial data and the source. A point here that saying that the solution y is in this space, that is the product of the rho 0 and the y is L2, means that in the final time t, the solution must be 0, since in the final time t, the weight is infinite. So this condition means that in final time, the solution of the system with a source that is in special space and weighted space can be controlled. Next, we remember our system that was in this way and was right in the vectorial way. We remember that we want to prove the new controllability of the system. Until now, we only prove the controllability with a small f here. Now we want to change the small f for this big F, this nonlinearity, the source for the nonlinearity. We'll do that using that the initial data is small enough. So we define the ball in the weighted space. And we have from the previous theorem that for each function on the ball, on this space, the associated control and solution has this kind of boundedness. Since we're assuming that the solution is small and the source is in a ball, we have an estimate for the solution, the control associated to the source in terms of some epsilon. So we can make this small enough. Well, we define, of course, the fixed point operator. So we can prove that it has a fixed point. That is that n small f is small f, and you can replace the small f by the nonlinearity. So we can prove the hypothesis of the Banach fixed point theorem and prove that the fixed point operator can map the ball into itself, and that is a contraction mapping. We do this by choosing suitable parameters A and B. Remember that these parameters are used to define the weight of the weighted space, and also using that the epsilon that is small and small enough. Applying the fixed point, we prove the result that under this assumption, the final result of these assumptions and small data, the temperature data, and a function close enough to the state of the boundaries, we can find the control here, only saying that it's null true, but we know that this control is a weighted space, a small part of null true. But what's important that you can't find a control that we drive the system under these assumptions to 0. That's the final result, the main result. If anyone has some curiosity, wants to see the technicalities, computations, one can see at the published work. And the time says to me that that's all. Thank you very much for your attention, for your interest.
Thank you very much. Thank you very much. It was a very clear, very beautiful presentation, and wonderful talk. And now we have time for 2 or 3 questions. So if you want to formulate a question, you can write, you can speak. Come on, Sylvain.
Yes. So first of all, thank you for your talk. It was really nice. I wanted just to understand, in the beginning, you were saying that your goal was to control only the temperature, right?
Yeah.
And at the end, if I am correct, you are controlling the whole state, right?
Yes.
So do you have any idea of what are the necessary and sufficient conditions to control only the temperature?
No, I don't have an idea about. If I understand well, we're saying too that we can not see what happens with the phase and control just the temperature.
Yeah. So in fact, I remember that there was some work in that spirit in the PhD of Michel Dupré, but I'm not sure to remember exactly what was inside. But I mean, certainly to control only the temperature, you will need less assumptions, right?
Right. Actually, the fact that we are trying to control both equations, well, we control the temperature. I don't know what would happen.
Okay, well, thank you. Well,
In fact, change a variable, it influence the solution. Yeah, of course.
Okay.
More questions? Excuse me.
I have another one. So in your model, you have many parameters, and in particular, you have this tau positive, the relaxation time.
They don't need to actually the term of the fuse. They don't need it to be the same. Actually, the right model, they're not the same. We make it the same. We make it the same to.
Okay, but I would like to focus on tau.
Right.
So what is the limit equation when tau goes to 0? Is it controllable or not?
Well, maybe, yeah, because if you see on the properties of you're asking for, if tau goes to 0, it maybe not be controllable. See, if in this condition, if tau goes to 0, you only have -2 rho, -1 to be different from 0, and there are values of rho that makes this condition equals to 0. So the problem is not controllable.
So you expect not to have uniform controllability, but what about the limit model? Do you think it is controllable?
I expected not to have control because of this condition, but it would have to be checked.
Okay, well, thank you.
More questions? Are there more questions? Yes, there's a question by Luis Yapu. One naive question. What is the interpretation of L and L star having eigenvalues of geometric multiplicity 1? What does mean? Which
Geometric
is the interpretation?
The L star are the operators that we, in the linear case, this case, making G of G equals to 0, to have geometric multiplicity one as the eigenvalues there are no eigenvalues equal. And the interpretation is just that if the eigenvalues are not equal, this expression is not equal to 0. It's what I meant when I said that this property, the eigenvalues L of L and star have geometric multiplicity 1, it's equivalent to this condition. This condition is exactly that one eigenvalue is different from other. Obtained by it. So the interpretation is that eigenvalues are different.
My question was if it implies why does it implies the approximate control?
Why this implies, right? It's associated with the dilemma. This. Here. If the eigenvalues are repeated. No, are you here? Oh. To apply this lemma, we need two eigenvalues to not repeat. Actually, this lemma is only needed, all these conditions only needed for having a B-orthogonal family with good boundary. But we don't need this all to the controllability property. We just need that the series converge and the eigenvalues are distinct. So we can have the existence of this B-orthogonal family. If we don't have the existence of this B-orthogonal family, that is, if the eigenvalues are, there's some eigenvalue that is equal to another one, we can construct a counterexample where the system is that does not satisfy the unique continuation property. It is. So, summarizing, if this operator doesn't have a geometric multiplicity 1, we have eigenvalues that are equal to each other, distinct eigenvalues that happen to be equal, and we can construct a problem that initial data that doesn't satisfy the unique continuation property. If you're curious, you can look at the work, the paper, and there we give the construction.
Okay, thanks.
I hope I had answered.
There is a question by Jean-Pierre Puel. That is there. Can you speak, please?
Yes. You have these conditions, these inequality conditions for the linear system. It might be that for the nonlinear system, even with if these conditions are not satisfied,
it would happen.
You could have controllability. Did you
we didn't
work on that or not?
No, we didn't check that. Actually, we didn't talk about that. But yeah, these conditions are all about the linear system. So we can use the techniques and have some answer for the nonlinear system. But it might happen that without, even with this condition, the the nonlinear system would be controllable. It would happen, maybe. It's an interesting thing to think about.
Any other question?
Yes. Do you hear me?
Yes.
Yes. My question is on the second assumption you had on the psi. You said that if it's not satisfied, then the eigenvalues are not separated. But
yeah,
in this case, can you measure how much they are not separated? Can you measure this concentration?
If it doesn't happen, the concentration would be zero. That they would be close. If it could be distinct, but sometime they would be getting closer and closer. And we need some separation to apply the lemma. We need always a good separation.
Okay. Okay, thank you.
Okay. One last question. It's someone ready for a last question? I will make a question. I will, for practical purposes, if you want to compute the control, have you any idea of what to do? Which is the how can you approximate the problem in order to get a control numerically?
Actually, I just talked with Pythagoras last night about that. I asked him if he wants to try to do this, because seeing that the control is computed from the B-orthogonal family, occurred to me that you can explicit expression for the control, but we would go after here's the control. We have the construction of the control, right? So we would go after of how we can write this B-orthogonal family. That is, how is this B-orthogonal family that goes from this lemma. And once you have this B-orthogonal family, you have the expression for the control, and you can apply it numerically. Right? I don't know if it's possible. It seems to be possible. My hope is that just the proof is also numerically applied. Reading the proof, I can see an explicit expression for this family.
Okay. Thank you very much. Talk. And, we have to stop now, and we see you all next week at the same time.